All right, now there's some other things that we learned in this chapter that we don't want to forget. First off, there is an inverse relationship. So the relationship between type 1 and type 2 is inverse, right? So that means that if alpha goes up, beta goes down. Alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. And vice versa. And it pays to write this down, right? If alpha goes down, beta goes up. Don't just write one of them, write them both. That way you can keep it straight. Now, alpha, this little one that looks like a fish, that's the Greek letter A, Greek letter alpha. It is the probability of a type 1 error, right? It is the probability of a type 1 error. And in medical tests, that's the probability of a false positive in medical screening. And beta is the probability of a false negative in medical screening. The false positive, false negative thing, it's really convenient language for medical tests. I find it to be inconvenient language for other types of tests. So testing for computer viruses, that's fine, but testing some other things, it's not as helpful. All right, now statistical significance. The word statistical significance means you get to reject HO, right? So that's what this means. Reject the null hypothesis. And remember, we always do that if your p-value is lower than your alpha. If your probability of getting the result that you got, or further along, is lower than the probability of a type 1 error right here. Now, practical significance is different. Practical significance is a judgment call based on context. And so what you kind of have to do is look at the problem. I have to write it correctly first. Look at the problem and compare your p hat to your p0. So I'll just make a note here. That's p hat to p0, or x bar to mu 0. And you see, hey, was this difference significant enough that it's real life significant? Practical significance is real life meaningful, right? That's what practical significance means. Is this meaningful for real life? And that's a judgment call we have to make. All right, some other pieces to remember about the p-value. So the p-value, I mean, what is it? It's the probability of a fluke. It's the probability of getting your sample statistic by random chance if your null hypothesis was true. All right. And when the p-value is low, we reject HO, right? So you want your p-value to be lower than your alpha, right? If your p-value is lower than your alpha, reject HO. We always want our p-values to be low. The lower, the better. What do I mean by better? The lower it is, let me just say, the lower it is, the more significant it is. More statistically significant. Practical significance is its own thing. There is one other piece to note here for p-value. The p-value is the area in the tails. Could be one tail or it could be both tails, depending on what it is, right? So if you think about the p-value as the area in the tails, it could be a z-score or a t-score, right? This is always 0 in the middle. The p-value is this area over here or this area over here. So you want your z or your t to be farther away. The farther away the z and t values are, the smaller the p-value is, right? So the p-value is the area in either one tail or the other tail or both tails. So the farther your z0 or t0 are from 0, because that's the center, the smaller the p-value will be. Because the p-value is the area in the little tails. If this z is farther out, it makes the tails smaller. If the z is closer in, it makes the tails bigger. So the smaller p-values will go with values that are far from 0, right? Z and t values that are far from 0, either direction. It doesn't really matter whether it's negative or positive. What matters is that it'll be far away. The farther it out is from the center, the smaller that p-value that's associated with that value will be.